In this video, we're going to focus on calculating the electric field due to a charged disk. We're going to derive the formula, and from that formula, we're going to come up with a formula to calculate the electric field of an infinite sheet of charge, and also the electric field between two parallel plates that contain a sheet of charge, an infinite sheet of charge. So we're going to do both of those, actually all three of those concepts in this single video. So let's go ahead and begin. So let's start with a disk. Now this disk is completely solid throughout. There's no open hole in the center. It's not a ring, but I'm going to draw an inner circle. We need to distinguish the inner radius and the outer radius. My circles are not perfect, but let's see if I can do that one more time. Okay, I'm just going to work with it. So our goal is to calculate the electric field from the center at some point P. So this is the inner radius, which I'll denote as lowercase r. And this segment here, that's going to be dr. So the inner radius is r, the outer radius is r plus dr. Now from this point to point P, let's call it L. And x is the distance between the center and point P. Now let's say if we have a small amount of positive charge in this region. That small positive charge will have a charge of dq, and you could treat it like a point charge. The electric field created by a point charge is equal to k times q divided by r squared, in this case L squared, since L is the distance between this small segment of charge and point P. Now that small segment of charge, dq, will create an electric field at point P known as dE. So dE is going to be k times dq divided by L squared. Now at point P, the electric field is directed in this direction. However, it has an x component, EX, and it has a y component, EY. Now EY is directed in the negative x-axis for a charge on the top. For charges on the bottom, it will create an EY that is directed in the positive y-axis. So these two vectors will cancel, and therefore the net electric field in the y direction will be equal to 0. So EY is 0. EZ is also 0. It turns out that the net electric field at point P is equal to the x component of the electric field. So therefore we need to calculate dE sub x. dEx is basically dE times cosine theta, where theta represents this angle. It's also equal to that angle. And here's the electric field E. So what is cosine theta? Cosine theta, according to the Soka-Towa thing, is equal to the adjacent side divided by the hypotenuse. So in this case, it's the ratio of x divided by L. So at this point, we can replace dE with the equation that we have here. We can get an expression for dEx. So dEx is dE, which is k times dq divided by L squared, times cosine theta, which is x divided by L squared. I mean not L squared, but just x over L. Now according to the Pythagorean theorem, we have a right triangle. L is basically the square root of x squared and r squared. So that expression will be useful shortly. So we can see that dEx is equal to k times dq times x divided by L to the third power. So keep this equation in mind. We're going to refer back to it. Now for the circle that we have, the area is equal to pi r squared. This is the area of any circle. So if we differentiate both sides, the derivative of a, or the differential of a, is dA. The derivative of r squared is 2r times dr. So we can say that dA is equal to 2 pi r times dr. So it's equal to the circumference, 2 pi r, times the width between the large circle and the smallest circle. Now we need to talk about sigma, which is basically the ratio between the charge and the area. So it's Q over A. And so for the small segment of charge that we had here, we could say it's equal to dQ over dA. The unit of sigma is basically coulombs per square meter. So if we rearrange this equation, if we multiply both sides by dA, we're going to get this expression. Sigma is equal to, well, dQ actually is equal to sigma times dA. So what we're going to do now is replace dA with 2 pi r dr. So dQ is 2 pi r times sigma times dr. So now we can replace this dQ with this expression. So now let's replace dQ. So dEx is going to equal k times x times sigma times 2 pi r dr. Divided by L cubed. So if we integrate both sides, the integral of dEx is simply equal to Ex. Now all of the constants we're going to move to the front. And for the circle that we have, we're going to integrate it from the center to the outer edge of the large circle. So that's from 0 to r. K is a constant. X, the distance between the center and point P, that's not going to change. As we integrate it from 0 to r, x is going to be constant. So we can move x to the front of the integral. Sigma is constant. That's the charge per unit area. And the 2 pi term is constant. So we have r dr. Now we know that L is equal to the square root of x squared plus r squared. So it's x squared plus r squared raised to the 1/2. So if we cube both sides, 1/2 times 3 is 3 over 2. So L cubed is x squared plus r squared, that's a terrible 2, raised to the 3 over 2. So now that we have that, what we're going to do at this point is we're going to focus on finding the antiderivative of this expression. So just jot this equation down and we're going to come back to it. So let's integrate r dr over x squared plus r squared raised to the 3 over 2. So we're going to use the u-substitution technique. So u, let's set it equal to x squared plus r squared. Since we have dr here, r is the variable, x will be treated as a constant. The derivative of any constant, like x squared in this case, is 0. So it's going to just disappear. The derivative of r squared is 2r times dr. So solving for dr, dr is du divided by 2r. So this is going to be r divided by u raised to the 3/2. And let's replace dr with du over 2r. So we can cancel the r variable, and the 2, let's move it to the front. Since it's on the bottom, it's equivalent to 1/2. Now we're going to take this u variable, move it to the top, which will change the exponent of positive 3/2 to negative 3/2 times du. So the antiderivative of u to the negative 3/2, you need to add 1 to negative 3/2. Negative 3/2 plus 1, which is the same as negative 3/2 plus 2/2, is negative 1/2. And then you need to divide by negative 1/2, which is equivalent to multiplying by the reciprocal of negative 2/1. So we can cancel the 2's. And what we have left over is negative u to the negative 1/2, which we can move the u back to the bottom. So it's negative 1 over u to the half, which is negative 1 over the square root of u. Now let's make some space. Let's get rid of a few things. At this point, we can replace u with x squared plus r squared. So this is equal to negative 1 divided by the square root of u, or the square root of x squared plus r squared. So now let's begin with our expression that we had last time. So ex, which we said was equal to 2 pi k times x times sigma integral from 0 to r divided by x squared plus r squared raised to the 3/2 dr. So this portion is equal to this expression evaluated from 0 to r. So ex is now 2 pi k times x times sigma, which is the charge per unit area. And then we have negative 1 divided by the square root of x squared plus r squared, evaluated from 0 to r. So we're going to begin by plugging in the top number. We're going to replace capital R. We're going to replace lowercase r with capital R. Lowercase r is the variable, x is the constant, so we can't replace the constant here. So if we plug in capital R, it's going to be negative 1 over the square root of x squared plus capital R squared. Now let's plug in 0. Let's replace lowercase r with 0. So it's minus negative 1 divided by the square root of x squared plus 0 squared. These two negatives will change into a positive. So we have negative 1 over the square root of x squared plus r squared, and then plus 1 over the square root of x squared. The square root of x squared is simply x. And since this is positive, I'm going to move it to this side. So I'm going to switch these two. So the electric field in the x direction is therefore equal to 2 pi k times x times sigma. And let's put this term first. So that becomes 1 over x minus 1 over the square root of x squared plus r squared. So what we're going to do now is we're going to take this x and move it in to the brackets. We're going to distribute it to the two terms inside. So x times 1 over x, the x variables will cancel, and you simply get 1. So Ex is now 2 pi k times sigma. X over x is 1, and x times what we have here, the x is just going to move to the top. So it's x divided by square root x squared plus r squared. So this is the equation in terms of k. And keep in mind, k is 9 times 10 to the 9. I believe it's like 8.99 times 10 to the 9, but you could round it to 9 times 10 to the 9. Now, most textbooks would write this formula in terms of epsilon sub naught. And k is equal to 1 over 4 pi epsilon sub naught. Epsilon sub naught is about 8.85 times 10 to the minus 12. So let's go ahead and replace k with this term. So the electric field in the x direction is now equal to 2 pi sigma times 1 over 4 pi epsilon sub naught times this stuff. So we can cancel the pi and the 2. 2 over 4 is basically 1 over 2. So now that gives us this expression. The electric field is now equal to sigma divided by 2 epsilon sub naught times 1 minus x over the square root of x squared plus r squared. So now let's apply this information in a problem. A disk of radius 3 meters contains a total charge of 480 nanocoulombs. What is the charge per unit area? So let's draw a picture first. So here we have a charged disk, and r is the radius, and some distance away from the disk, let's say point P, we wish to calculate the electric field, which we know is going to be directed along the x-axis, away from the center. Now the distance between the center and point P is 25 centimeters. Keep in mind, this picture is not drawn to scale. So with this information, how can we calculate the charge per unit area? So let's write down what we have. So we know that R is equal to 3 meters. The total charge Q is positive 480 nanocoulombs. And X is 25 centimeters, or 0.25 meters. Now sigma, which represents the charge per unit area, is Q divided by A. The area of the disk is basically pi r squared. So therefore, the charge per unit area is going to be 480 times 10 to the negative 9 coulombs. Nano is 10 to the minus 9, divided by pi times 3 meters squared. So let's go ahead and calculate the answer. So let's type in what we have. The answer that I got is 1.697 times 10 to the negative 8 coulombs per square meter. Hopefully you got the same thing. Now that we have the charge per unit area, let's go ahead and calculate the electric field. So what equation do we need? We can use the equation that we came up with a few minutes ago, particularly this form. It's sigma divided by 2 epsilon sub naught times 1 minus x divided by the square root of x squared plus r squared. So now we just got to plug it in. So sigma is 1.697 times 10 to the negative 8, which got cut off, divided by 2 times epsilon sub naught, which is 8.85 times 10 to the negative 12, and then it's 1 minus x, x is 0.25, divided by the square root of x squared, 0.25 squared, plus r squared, which is 3 squared. So you can type this whole thing in a calculator, but for those of you who may not have an advanced calculator, I'm going to do most of this step by step. So 1.697 times 10 to the negative 8 divided by 2 and 8.85 times 10 to the minus 12. So this section right here, that's equal to 959.1. 0.25 squared plus 3 squared, that's about 9.0625. The square root of that, it's 3.0104. 1 minus 0.25 times 3.0104. That's about 0.91695. So you should get a final answer of 879.5 newtons per coulomb. Now it turns out that we can actually get the equation to calculate the electric field produced by an infinite sheet of charge. Even though we're starting from a disk, if we increase the radius of the disk such that this object becomes infinitely large, the shape of the object is no longer important. It turns out you can still get the right equation to calculate the infinite sheet of charge, or the electric field created by an infinite sheet of charge, starting with this formula. So let's go ahead and do that. Now, as the disk becomes very, very large, we need to realize that r approaches infinity. So let's focus on this expression. What is the limit as r approaches infinity for the expression x divided by the square root of x squared plus r squared? Now keep in mind, x is a constant. So if we replace r with infinity, what's going to happen? So we're going to have infinity squared. A finite number plus an infinite number is going to be an infinite number. If you add, let's say, 5 squared plus 1,000 squared, 1,000 squared is about 1,000,000. 5 squared is 25. 25 plus 1,000,000 is 1,025,000, which rounds to 1,000,000. So x becomes insignificant. So we can say this is approximately equal to the square root of infinity squared. The square root of a number squared is equal to that number. And if you take a finite number and divide it by an infinite number, or if you take a small number and divide it by a large number, it's going to approach 0. For example, 10 divided by 1,000 is 0.01. 10 divided by 1,000,000 is even smaller. That's like 0.00001. So this approaches 0. So as r becomes very large, this term approaches 0. So Ex is now equal to sigma over 2 epsilon sub 0 times 1 minus 0, which is therefore equal to sigma over 2 epsilon sub naught. So this is the electric field created by an infinite sheet of charge. And that's the equation. Go ahead and try this problem. What is the electric field produced by an infinite sheet of charge that has a charge per unit area of 5 microcoulombs per square meter at a distance of 50 centimeters and 5 meters away from the center of the plate? So let's draw a picture. So we're going to draw a very large rectangle. And that rectangle has a positive charge that is distributed uniformly around the plate. We wish to calculate the electric field at some point P. So initially at 50 centimeters away. So the equation that we can use is this equation, the electric field, which is directed away from the plane of the plate, in this case, in the x direction. The plane of the sheet of charge is in the YZ direction. It's in the YZ plane. So the electric field is perpendicular to the YZ plane. So it's in the x direction. And it's equal to the charge per unit area divided by 2 times epsilon sub naught. So we have the charge per unit area. It's 5 microcoulombs per square meter, or 5 times 10 to the minus 6 coulombs per square meter, divided by 2 times epsilon sub naught, which is 8.85 times 10 to the minus 12. So it's a very simple formula to use. So I got 2.82 times 10 to the 5th power newtons per coulomb. So that is the electric field produced at some point P. Notice that for this equation, we didn't have to plug in the 50 centimeters or the 5 meters. The electric field is independent of the distance between the plate and point P. Since the plate is infinitely large, x is insignificant. So the distance doesn't matter. There's no x in this equation when you have an infinite sheet of charge. So the electric field is simply sigma divided by 2 epsilon sub naught. So it's independent of the distance. So for part A and part B, the answer is the same. Now, what is the electric field between two infinite sheets of charge? So let's say if we have parallel plates, one is negative and the other is positive. So what is the electric field inside between the two plates and outside of it? Let's call this sheet 1 and sheet 2. So sheet 1 will create an electric field that is directed away from the positive charge. So let's call that E1. Sheet 2 will create an electric field that is directed towards the negative charge. As you recall, the electric field always emanates away from a positive charge, but towards a negative charge. So the electric field created by sheet 2 is going up towards the negative charge. So as you can see, the net electric field between the two plates is the sum of E1 and E2. Now what about above the negatively charged plate? The electric field created by the positively charged plate will still be in the upward direction because it's going away from the positive charge. E1 will continue to go this way. And what about E2? The electric field created by the negatively charged plate is directed towards the negative charge. So at a point above the negatively charged plate, it's going to go towards it, so it's going in a downward direction. Now, because the electric field of an infinite sheet of charge is independent of the distance, E1 and E2 have the same magnitudes. So the net electric field, which is the difference between E1 and E2, is going to be 0. If you have two numbers that have the same value, and if you subtract them, it's equal to 0. 10 minus 10 is 0, 5 minus 5 is 0, so the net electric field outside of it is 0. The same situation applies below the positively charged plate. E1 is going to emanate away from the positive charge. so it's going in the negative y direction below the positively charged plate. E2 is directed towards the negatively charged plate, and so it's in the positive y direction. So the net electric field is going to be E2 minus E1, which, because they're the same, it's still equal to 0. So whenever you have two infinite sheets of charge, the electric field outside, above it and below it, is equal to 0. However, the electric field inside is the sum of these two values. Now we know that the electric field due to one infinite sheet of charge is the charge per unit area divided by 2 times epsilon sub naught. So therefore, the net electric field, which is the sum of the electric field of two infinite sheets of charge, is going to be E1 plus E2, or sigma divided by 2 epsilon sub naught plus another sigma divided by 2 epsilon sub naught. Sigma plus sigma is basically 2 sigma. And so we can cancel the 2. 2 divided by 2 is 1. And so the net electric field in between two infinite sheets of charge is simply the charge per unit area divided by epsilon sub naught. So you know how to use this equation in the problem. So that is it for this video. Thanks for watching, and have a great day.